The next sorting algorithm we're going to look at is called insertion sort. We're back on the Geeks for Geeks website, and we're going to look at an example they have of an insertion sort run over a list. So the top row here is their starting list, and the green value is the first value that they're looking at, and then it advances with an inner loop the same way that the bubble sort has an inner loop. So first they check, is 3 less than 4? They compare these two values and see if they're out of order. And if they are out of order, they keep checking further to the left until they find the correct position for this 3. What's going to be true of insertion sort is that all the values before the green value are going to be sorted in order. And on the next loop, they're going to start with this number 2 right here, and they're going to compare it to the previous values and put it in the location that it needs to go into. So they compare these two and realize it needs to go right at the start. So now these values are all in order. They're going to look at the next value, compare it to everything that came before. Well, it's actually already in its correct location. So they look at the next, and these red values are the ones that they're going to need to move this value past. So the 1 needs to go all the way back to the beginning, but here on this line, the 5 needs to only go 2 places to the left. Here's the Geeks for Geeks insertion sort algorithm written in Python. There's an outer for loop right here that loops over the length of the list. Notice it starts at index 1, not at index 0. That's what we were saying before, where we started with the second value in the list, and we're going to compare it with everything that came before. The reason we don't start with the first value in the list is because there's nothing that came before it, so we know that we don't need to sort nothing. Now this is the inner loop right here, where we're going to be, we're going to start with the previous value compared to the one we were looking at, right? We're currently looking at that green value that we showed in the previous chart, and then we're going to go 1 index to the left, and we're going to start comparing with those values to the left. As long as the index is greater than or equal to 0, and the value we're currently looking at is less than the values we're comparing to the left, then we need to keep moving to the left and keep comparing to further to the left items. It really helps us out in insertion sort that all those values to the left of the key, that green value, are already sorted, because that makes it so that we don't worry about having to compare to all those values. We just start at the biggest value and move left until we find the location that we're going to put our current value into. So let's look at how insertion sort stacks up on those same metrics that we looked at on bubble sort. Now this is actually poorly written. This is not n times 2. This is n squared. The worst time complexity for insertion sort is actually the same as bubble sort. In the worst case and in the average case, insertion sort is actually as bad as bubble sort. Although many times with real world data, insertion sort is going to be quite a bit better. In terms of extra memory that needs to be used, well, it's order 1 as in constant. So there's very low extra memory that is needed. The boundary cases. So insertion sort takes the most time if the elements are sorted in reverse order. And this is actually the same worst case scenario as bubble sort. It takes the minimum amount of time, and it actually just takes order of n, as in linear time. So it takes about the same amount of time as the length of the list itself. So if you have 10 items, well, it takes 10 units of time. And that unit depends on how fast your programming language is, for example. And that occurs when the elements are already sorted. So like bubble sort, insertion sort is very good when the elements are already sorted. The algorithmic paradigm, we didn't see this with bubble sort, but insertion sort is an incremental approach. We're slowly going to build towards the best solution. And that's actually the same with bubble sort, even though we didn't see this written down in terms of bubble sort's properties. Does it sort in place? As in, does it use the same memory? It doesn't copy everything to a whole new list? Yes, it does. Is it stable, meaning it's not going to change adjacent values that are already equal? It's not going to swap those values? Yes, it is. Online. We didn't see this before with bubble sort, but online basically means, can you feed the values to insertion sort one at a time rather than having to give it the whole list? And can it then sort the values one at a time? And yes, it can. So what we would do then is each new value we would get, we would pretend that that was the next item in the list, and all our previous values should already be sorted, so we would just go back through our list and find the location that this newest value should be put in, and we would put it there. So even though insertion sort doesn't have any of these values that look a whole lot better than bubble sort, it is actually quite an improvement when we're actually running it on real data. So let's see what it looks like with some cards. The 10 is going to be our key, that green value that we're going to compare with the previous values. It's greater, so it doesn't need to have any change. Now the 2 is our key, and let's look at what happens next. The 10 gets copied over to the 2's location, and now the 2 is getting compared to previous values. You might not have noticed that initially in the code, but this is actually an important piece. So let's pause this and talk about it for a second. So the copy occurs on the line where we have ARR, and that's the name of our list. It's short for array because we could be sorting an array. So array at index j plus 1 equals array j. So we're copying the value from array j location, the previous location, to the forward location j plus 1. That's the copying that I'm doing. So please keep an eye out for that as I'm sorting with the cards. You'll see me copy one card to the next card in the list. The reason I can do that without losing track of the key is because I've actually saved the key in another variable. That's the variable named key that you can see in this code. Back to the sorting. So now 10 is my key. I compare to what comes before, but it's already in order. Now 5 is my key. I compare. I need to copy that 10 to the forward location and compare the 5 to the previous values. Now 5 is greater than 3, so I know the location is that 10 spot, and I can just copy it over safely because I've moved the 10 forward. Now 9 is my key. I copy the 10 forward, compare to 5, and I just put that 9 in the location where the 10 was. So there's not actually any swapping that's going on in insertion sort. There's just this copying forward of values, and I'm going to keep copying forward until I find that location where the current key should end up in. So 4 compares with 10, 10's got to be copied forward. 4 compares with 9, 9's got to be copied forward. 4 compares with 8, 8's copied forward. 4 compares with 5, 5's copied forward. 4 compares with 3, and now we're good to go. And since there's 2 5s, I just pop that 4 right into one of those locations and I don't lose any values. Now I'll let this just run out to the end and I'll put up the total number of comparisons. We've completed our insertion sort with only 24 comparisons. If you look back at the bubble sort video, you'll notice that sorting the same number of cards took 36 comparisons. Now we should be careful to compare these single pieces of data, right? I mean, depending on how sorted the lists were to begin with, we'll change the number of comparisons. But it's worth noting that our insertion sort did a little bit better, and in general it's a slightly better algorithm than bubble sort. But soon we're going to see some real power players that are much better.